My name is Alan Baxter. I'm a research associate with Metal Oceans. We're going to go back to the modern for this talk. It's just a little review on the cruise that we went on, myself and Mark went on last year, and also some preliminary insights, potential analogues with some sedimentary analogues with some of the Archean sediments we've been talking about. Just like to acknowledge the project research and funding partners. So the outline of the talk is to really talk about syn-collisional setting in a modern back-arc basin and how this setting is evolved over, how its back-arc crust has evolved over time. I'll give a little summary of the expedition that we went on in June and July of this year to the New Ireland Basin. And on that cruise, we start thinking about the sediments that were being deposited in that region, and started comparing those to potential sedimentary analogues that we see in the Abitibi. Maybe not in the same tectonic regime, depending on what model you're talking about, but in terms of the sedimentary facies and maybe the relationships between the rocks that are being emplaced and intruded around the modern area. So again, Mark went through this and everybody else. We study this area because it is the most likely analog to Archean processes that we can find. It has the fastest crustal growing crust on Earth, an area of massive extension, even though we would call it a convergent margin. The convergent margin areas are really thin areas around the subduction zones, but hyperextension in this area is key for the evolution of this crust. As Mark said, nearly a third of all hydrothermal systems on the Western Pacific are found in the Northeast Louth Basin, but also in the Manus Basin, where I'll talk a little bit about later on. And also it has some of the most richly endowed crust, including 3 of the top 10 copper-gold deposits in the world. This kind of plot, or this kind of thinking has kind of evolved over the last couple of years to try and understand how back-arc crusts evolve. So in order to kind of figure out what happens to back-arc crust from when it's initially formed all the way until it's terminally collided in a orogenic setting, you have to think of it in different stages. So this is just something that I put together to talk about the evolution of crust in 3 different stages, namely a pre-collisional stage, a syn-collisional stage, and a post-collisional stage. In the pre-collisional stage, you're talking about arc building, then that arc becomes unstable, and due to subduction rollback in modern settings, you get arc rifting and back-arc basin formation. And associated with all those processes, you get structures and magmatism and mineralization events that occur during that stage of the evolutions of the life cycle of back-arc crust. Then you can move to a syn-collisional stage. This could be defined by a collision that occurs, a major collision that occurs that can change the tectonic stress regime. Again, you get new structures forming, you get reactivation of structures. Maybe they were extensional and they've turned into transcurrent structures. You'll also get new magmatism, and you'll also get mineralization events associated with that. And then the third is the post-collisional stage. This is terminal collision in the modern environment, where you get uplift, erosion, partial preservation. And what's key here is that at each stage of this evolution, you get increasing complexity and inheritance. These structures don't just disappear; they are activated. They're developed, activated, and reactivated over time. So we're going to focus in on just the syn-collisional stage for this talk, because that's where we went on our cruise. But as you've heard from previous Metal Ocean speakers, we spent a lot of time in the pre-collisional stage. We're kind of working in the syn-collisional stage at the moment, and then hoping to tie in the post-collisional stage so we can learn about this life cycle. So we're going to go all the way to PNG and the northern margin of the New Guinea island. Again, a really complex area of microplate dynamics. When you compare the hyperextension that you see in the Louth Basin, which is dominated by extensional structures like spreading centers, and also transcurrent faults like Peggy Ridge, or the step fault that Mark talked, the Futuna deformation zone that Mark talked about. In this syn-collisional setting, there's more convergence and transcurrent motion. So there are extensional spreading centers that you can see in the Manus Basin, for example, or in the Woodlark Basin to the south. But overall, you're talking about oblique convergence and transcurrent motion. And also, if you think back to the map about the Lau Basin, you can see that this type of crust that's involved is, there's a lot of different types of crust, but in general you get arc crust and back arc crust. In this syn-collisional setting, you're starting to get a diverse array of different crusts. This could be mid-ocean ridge crust, oceanic plateaus, forearcs, back arcs, relict arcs, relict forearcs, microcontinental fragments from Australia in this example. So there's a huge range of new crust that is being incorporated into this syn-collisional setting. This is an image just of the second map that was developed at the 1:1 million scale. This is of this area that I'm talking about, the syn-collisional and post-collisional stage of our modern analog with the Abitibi. And you can, as Mark said, for the Lau Basin, there was about 40 formations defined for the Lau Basin. Here we can see a legend on the left-hand side on your screen where we have about 60 or 65 different formations, and that just reflects this diversity that we're talking about. So much more complexity, much more diversity. You get new structures being formed, new magmatism, all in this area. Just to say a little bit about the tectonics in the area, because it's important for those that are unfamiliar. To the right-hand side in here, this is the Ontong Java Plateau, and this is one of these major events. The collision of the Ontong Java Plateau with the Melanesian arc is one of these major events that define this as a syn-collisional zone. You had the Ontong Java Plateau being introduced into the Vidyas subduction system, and because it's 30 to 40 kilometers thick, you cannot subduct it anymore. So what happened was you have a subduction polarity reversal where subduction swaps orientation, and now you have subduction along the San Cristobal Trench, which is here, and the New Britain Trench, which is here. So within the past 10, 15 million years, you've had a complete revamp of the tectonics, and this has a profound effect on what's happened in terms of crustal growth, magmatic productivity, crustal permeability, and metallogeny as well. And just to highlight that you even have in the Woodlark Basin here, as I mentioned previously, that you even got Morb signatures, a full basin that is a Morb signature in this convergent margin. So it kind of reflects the complexity that Mark was talking about Mark Fassbender's work. You can just get so many different environments in such a small area. Just to shoot up to the area that we worked in over the summer, this is in the red box up here in the New Ireland Basin. The New Ireland Basin initially developed as a forearc to the Eocene. This was before the collision of the Ontong Java Plateau. When the Ontong Java Plateau collided with the subduction zone, it changed from an active forearc to a relict arc, and this was about 15 to 20 million years ago. And so in this area is what we refer to as the New Ireland Basin. If you go just about 100 kilometers or 50 kilometers to the east, you have the Eastern Manus Basin, and this is an arc rift where you have SMS deposits forming as part of the Solwara copper gold deposit, and then you have the New Ireland Basin, which is this long, thin island, the New Ireland Island, which is this long island that you see here. This is being moved along a left lateral strike-slip fault referred to as the Y10 fault, and it's actually moving the island of New Ireland off to the northwest. In the basin, you have these 4 islands referred to as the TLTF islands, the Tabar, Lihir, Tanga, and Feni Island. And one of these islands, Lihir, hosts the Latolum deposit, about 50 million ounces of gold as a porphyry epithermal system. And I like this plot on the right-hand side just because it shows how you can have very different ore-forming systems. You can have an SMS, a C4 massive sulfide deposit about 100 kilometers away from a porphyry epithermal system in a completely different environment, separated by a major transcurrent structure in the case of the Y10 fault. So this was kind of the reason why we wanted to go to this area, to understand the relationship between the crustal architecture and the metallogeny. So in June and July of last year, myself and Mark went to Townsville We jumped on the RV Sana, which is this 120-meter vessel from a German research vessel, one of the best research vessels out there. And we aimed, the cruise really aimed to study the links between geodynamics, metallogeny, with a special emphasis on the gold-rich mineralization on and in the vicinity of Lihir Island. There was about 36 scientists on board, 11 different institutions, people from Canada, from Germany, from Finland, Costa Rica. And some of the research questions that we're trying to answer is, what are the consequences of the most recent subduction reversal and the microplate rotation that you see in the microplate map? How is crustal structure linked to metallogeny? And what is the nature of the magma plumbing system in the TLTF islands? There were 4 work areas that we went to. The first is the Y10 fault. This is this left lateral strike slip fault that cross-cuts the New Ireland Island and links the Eastern Manus Basin with the New Britain Trench. So it goes from the Eastern Manus Basin here, down along here, and then intersects with the New Britain Trench in here. It hadn't been mapped offshore before. It's been well documented onshore, but there was no understanding of the fault as it moves offshore towards the New Britain Trench. We then worked primarily in the New Ireland Basin around the island of Lihir, looking at the links to the metallogeny that's occurring there and collecting lots of samples for geochemical analysis. There were 2 other minor areas that I won't really talk about, the Manus Keelan Trough, where we looked at this inactive subduction zone, and then this cryptic structure up here, the Musau Trench, which is supposed to be a site for a subduction initiation within 2 oceanic plates. And we took a couple of samples and are doing some work on that for the future. So the completed program that we did during the cruise was, there was 177 stations, about 5,000 line kilometers of hydroacoustic and gravimetric surveys. There was about 18 ocean bottom seismometers and 16 ocean bottom magnetotelluric systems deployed, and all of them were recovered, thankfully. There was heat flow stations, and in terms of sampling, we did 12 dives with the ROV Keel 6000. We had 16 stations with a TV-guided grab. We took sediment samples from the gravity core. We did lots of dredging all different parts of the crust to try and get a representative sample for that represents the diversity of the different rock types you see. And that totaled to about 450 rock samples. There was also fluid samples, sediment samples, and water samples as well taken. As part of my responsibilities on the ship, I focused on the acoustic data collection and also the sub-bottom profiling data collection. You saw this briefly in Mark's talk, where the parasound data that you can see here, this can help us understand the sedimentation, the recent sedimentation, looking in from about 0, the sea floor, to about 200 meters, but generally about 100 meters or 50 meters. Some of the things that we were able to confirm by looking at some of these profiles is some of the tectonics that are supposed to control magmatism, or have controlled magmatism in the recent past. So in the case here, there's a small tectonic horst, and along that horst, you can see it here, along that horst block is some submarine volcanoes. So you have active magmatism coming up through these pathways, and these are also implicated, or similar structures are also implicated in the development of these and formation of the TLTF islands. There was lots of different types of sediment that we looked at, including hemipelagic sediment. We found some turbidites. This is just an interesting aside here, that in a modern, in a recently active volcano, all around the island we found these acoustically transparent units, and we interpret these to be mass flow deposits or flank collapses. And you can even see on the bathymetry here, there's these large blocks that are offshore of the Ladalam deposit, which is just here. And these are large blocks that have just shot out into the basin and probably contain a couple of million ounces of gold as well, sitting down there. I mentioned that this basin is about, let's say, 15 million years or so, but there's about 6 kilometers of sediment being collected in this basin. So even in this convergent region, you're still getting a huge amount of sediment being input. The main sediments that you find in this basin are turbidites, conglomerates shed from the New Ireland Basin. Then you've got the mass flow deposits from the islands. You also have limestones being some lower level limestones that are accumulating as well in the shallower regions. This is just an interpreted seismic image that was taken. The seismic image was taken about 20 years ago, I think, and just shows you the thickness of the sediments. And more recent exploration for oil and gas has got new seismic that we're not allowed to show, but they also show, I've seen intrusions and sills in this. So we have a full basin that is actively, that has been intruded in the past, and with active hydrothermal activity on some of these islands, and porphyry epithermal systems that are not that old as well. So these are just some of the sediments. As I said, it really, the triggering of the New Ireland Basin filling occurred in relation to this Ontong Java arrival and the subduction reversal, and then you get this sequence of sediments that have been accumulated, about 6 kilometers of sediments in the last 20 million years or so. So these are sediments like, as I said, turbidites, conglomerates, hemipelagic sediments and limestones, and they're intruded by alkaline magmas in the TLTF islands. And then you also have some adjacent submarine volcanoes that are basaltic and andesite that we dredged during our cruise. This just reminded me from some of the talks about the Pontiac. It seems that, I'm not saying that it's the same, but maybe in terms of the sedimentary facies, it's similar, and also in terms of the relationship, the syn-magmatic intrusions and volcanism that is happening there. I mean, there's clear differences between them, but if you're trying to look for a modern analog for the Pontiac, it seems like this would be a good place to kind of look to better understand the sedimentological processes and maybe even the interaction of the sediments with the melts that are coming through. So it's just another comparison that we're trying to make, is we're trying to link what we see in the modern with some of those features that we see in the Abitibi. In addition to the sediments that we see in the New Ireland Basin, as I was reading and getting to know more about this area, I came across the Maton conglomerate. This is a pebble, cobble, and boulder conglomerate. This sits within the transcurrent fault along the Y10 fault. So this is the Y10 fault here, and you get these pebble and boulder conglomerates that sits there. And you also find them on the opposite side, on the New Ireland side, where they're supposed to be, or interpreted to be, upper fan channel subaerial debris flow deposits and braided streams. And again, this kind of just reminded me of a Temiskaming-like sediment, and I like this sketch. Again, reading Richard Hyde's paper in 1980, where you have a narrow shelf, you've got some volcanic rocks, and then you've got these braided river system facies that are on shore, and then you've got turbidites flowing into the basin with active volcanism as well. And you can see that this is here, where you have near a million years or a couple of million years ago of active volcanism. You've got active volcanism or near active volcanism in the basin. You've got, and these conglomerates are forming now in this area. So hopefully we're going to continue working on this in this region. Again, a really complicated area. They're very dynamic in terms of crustal architecture, magmatic permeability, magmatic productivity, and metallogeny. And we're trying to better understand how these major structures can control the metallogeny. So some of the things that we're trying to do is just some of the people who been on the cruise as well, is to try and look at the source of the magmatism, whether it's related to the slab that's being subducted along the New Britain Trench, or whether it's some residual melt that comes from the slab that used to be there, the subduction, active subduction there, or some other area, some other place, some other source. We're also really interested in this question on why do we have ore forming systems that are apparently separate, but they're really close together, and in fact, is there any link between those major transcurrent structures that we see, such as the Y10 fault, if they have any direct relationship between those ore forming systems? So for my post-cruise objectives is to map some of these structures offshore and to better understand the regional tectonic evolution, and then produce a structural map by classifying the structures based on their morphology, offsets and known movements. So similar to the work that was shown earlier about trying to use the data sets that we have to better understand the evolution of this syn-collisional setting, and then try and merge that with some of the work that the petrologists and geochemists are doing on the sediment and rock samples that we've collected last year, and then try and come together and try and better understand this system as a whole. Okay, I'll leave it there, and if you have any questions.